Welcome everyone. We'll give folks a few minutes to kind of filter in here and we'll get started shortly. All right. Well, thanks everyone for joining us and welcome. My name is Aaron Menza and I'm hosting today's session on behalf of the Minnesota GIS LIS Consortium. We're excited to welcome you to another installment of mAppetites. This is our lunch hour series focused on sharing bite-sized personal insights related to the geospatial industry. Today we're excited to welcome Roger Schulz. Um, Roger is the Director of Geospatial Technology at Vertex Unmanned Solutions, where he leads the company's geospatial strategy with a focus on delivering and supporting GNSS hardware solutions. He brings a diverse background spanning utilities, consulting, mining and exploration, GNSS support and training, and local government GIS coordination. Throughout his career, Roger has focused on improving geospatial accuracy, ensuring data integrity, and developing practical, scalable workflows that support users across all technical levels. His experience enables him to bridge the gap between advanced geospatial technologies and real-world applications, helping organizations implement efficient and reliable solutions. At Vertex, Roger is dedicated to advancing geospatial capabilities and empowering teams to make better data-driven decisions through precise and dependable GNSS and GIS solutions. And with that, I will turn things over to Roger for his presentation on enhanced GIS data collection with GNSS sensor tracking.
Thank you so much, Aaron, and a lot of acronyms there. Well done. Got through all the G's and N's and S's and everything else in between.
I had to slow down and take a breath.
Absolutely. Yep. So today, let me see here, make sure I am sharing the right screen. Beautiful. Everybody got me there? Sweet. All right. So, of course, we started on the wrong slide. Let's back up. Whoa, hello. Love it when technology works. All right, so welcome. This is enhanced GIS data collection with GNSS sensor stacking. So the big thing we want to talk about here is a lot of hardware stuff. So we're going to start from the top and work our way through this. But let's get a little bit of background on who I am. Thank you very much, Aaron, for reading, the bio. A little bit of buzzwords and stuff in there, but at the big root of it, I've got a diverse background in geospatial technology. Geospatial has always been something I've been connected to, whether it's discipline specific or something more directly GIS specific. Graduated from Eau Claire, got the opportunity to work with some utility companies, got to work with other high accuracy GNSS distributors. I worked as a consultant for Big Rock Exploration in the mining and exploration sector for a while. I had the absolute privilege of being able to work with the city of Blaine most recently, and now I have the pleasure of working for Vertex Unmanned Solutions. That's kind of a little bit of my history and background and where things come and where a lot of my exposure to a lot of different industries has come from. So, what GPS should I use? We're all GIS folks here. We're all GIS users, but how many of us are GPS or GNSS users? But I guarantee almost all of us at one point in our career have had this question come up. GIS staff know absolutely everything that has to do with a map, right? We know everything. Sure, you get the grandparents that are asking you, how do I use MapQuest again? I don't know. I haven't opened that up since about 2004. So, but it's a map, right? We should know it. We're GIS folks. And sometimes the field staff and people in our departments ask us, "Hey, what GPS should I use? What should I use to get a position out in the world?" These are questions that come our way, and yet how often do we see GIS folks out in the field? Normally, we're stuck behind our cubes and fully nerded in on making sure our projections are right, our coordinate systems are right. And is that blue blue enough, or should I make it a little bit brighter blue? Is everything ADA compliant with the size of my font? Buzzword nowadays with ADA compliance being a big thing coming up and being required across a lot of state stuff. So those are the things that we're normally focused on, getting our maps published, getting them online. How often do we work with field data collection? For some of us, it might be a lot, but for some of us, it might be almost never. So today I want to take the opportunity to nerd out a little bit with you guys. And remember that GIS doesn't stand for Get It Surveyed, although I work with a lot of surveyors who like to say that. It's okay. We know what it means. And so today we're going to nerd out on hardware. We're actually going to talk about modern GNSS solutions and take a deep dive into what components are included and how they work together and what makes a modern solution different from something you would have seen in the early 90s. The other thing I want to really focus on in here is a lot of times I've been training, and as I've been training on GNSS solutions for over the last decade, a lot of times the focus has been on that GNSS 101. How does the system itself work? How do we get a position, satellites, differential corrections? If that type of conversation is something you're interested in learning about and hearing about, I would love to present on that at another time if that's something you're interested in, if it's a story you haven't heard, if it's something you haven't heard in a long time, or if it's something you'd love a refresher on. I'd love to chat about that. But I think the one thing that we haven't talked about a lot is the actual hardware itself. What is involved inside our GPS, our GNSS systems? And so today, that's what we're going to take a peek at and take a good look at. What is inside each one of our receivers and how does it work and what makes it a modern solution? So one of the big things that has been a game changer over the years is smartphones and tablets. They all have some form of GNSS integrated, and it's been a huge game changer. How many of us are using field maps or Survey 123 or had been using other different applications to get positioning live in the field, be able to update our maps live in the field, get GIS data instantly, have field users actually contributing into GIS? Nowadays, you actually have staff that know what GIS is. It's really exciting. I just, was down at the car shop getting my car worked on, and the guy that came out to help me work on my car was like, "Hey, so what do you do professionally?" I mentioned GIS, and he's like, "Oh, I know GIS. I was exposed to that when I was in the military. This is really cool." So GIS is now starting to become more commonplace. We're seeing it out in the public, and people are doing GIS without even realizing it. And a lot of that has to do with a bunch of integration with smartphones, with tablets, with the internet, and having access to our data live anywhere we are. So our phones have a bunch of different things going on in them. They have GPS and GNSS built in. They've got a camera. They've got different apps. They've got different sensors. Little foreshadowing here. This is an example of sensor stacking. Your cell phone has got tons of different things integrated all together that are working together to give you a better solution than we used to have with like the old bag phones back in the day where they had one function: pick it up, make a phone call. Nowadays, our smartphones, our phones, are much more complex than that and do a lot more for us. But sometimes precision matters more than what we can get on a phone and a tablet. And this is something I know that's been preached a lot, especially over the last 10, 20 years. When does precision matter? And I think these are just some great examples that we can run across. We've got utilities and things that are located really close together. Um, what is your map actually showing you? As we all know, as GIS folks, every map we've ever built is completely wrong in some way, shape, or form at some level of detail. There's always something kind of wrong in it. But how wrong is it? Is it actually an accurate representation of what we actually see in the field? What was the source data behind that map that you have? Working with several different, cities and municipalities and utilities, sometimes those maps are generated from as-builts. And that can be great. That was a great source of data. Was that as-built actually what it was in the field? Is that utility really on the right side of the road? I do know that there are cities where things aren't really where you thought they were. And if you look at your GIS, it'll show you a basic representation of where things are, but you might be off by a long, long distance. So accuracy can matter, especially when you've got people that are going out and need to locate something. And let's be honest, here in Minnesota and Wisconsin, we get snow, we get ice, we get buried, and finding a buried utility can certainly be a challenge. And so making sure that we're accurate can really save a lot of folks a lot of headache. And there's also that futuristic thinking. Where are things going? And where are things currently? We can do augmented reality and visual data capture. And if our data is accurate, now we can actually do it with confidence and see where things really are as they truly relate to reality. So, sensor stacking. What is sensor stacking? So, sensor stacking is hardware and software that are multiple different distinct sensors that are assembled and work in concert in one common set piece of hardware, piece of equipment. Sensor fusion, another buzzword, is the mathematical and algorithms that process and continually combine raw data from these multiple different sensors and fuse them together to all work together in harmony. So we can stack different sensors into one unit, and then we can make them work in harmony by using this sensor fusion. So today we're going to go through and we're going to chat about a couple of things that are in modern GNSS receivers. We're going to talk about components like the OEM board and what's on that board, what N-trip components might be in a GNSS receiver, if it has an integrated radio, what that means and how that can benefit us. And even some newer ones are adding things like a camera. And what benefit does that have by having a camera on our receiver? So let's look at the OEM board itself. So like I said, we're going to talk about hardware. We're going to go right down to the actual chip itself. So this board is a board that has multiple different components attached to it. OEM, if you don't know, stands for original equipment manufacturer. So there's going to be a board that is built by some company that then has a bunch of things stacked on top of it. So the board itself is important. That is a very important part. It's like a motherboard on a computer. Without that motherboard, your GNSS receiver obviously can't operate. But there's a bunch of things in this board. It is the brains and that central nervous system and the hub for stacking a bunch of different things that all integrate and work together at that microchip level. So it's also where we can install and utilize both that hardware and that software side. So we've got that engine inside that's fusing everything together. This is where, that fusion really takes place. So almost all that fusion happens right here on the board level. So let's take a look at some of the components within an OEM board. So inside an OEM board, on a GNSS receiver, you're going to have that GNSS chipset. So I keep using this term, GNSS, just want to make sure everybody's familiar with it. Global Navigation Satellite System. What this means is it's all the different GPS, GNSS, all the satellite networks that are out there that give us a position. GPS, being the American one, is the one that we're most familiar with. It's kind of like why we use the term, just what's your GPS? Well, in the old days, it used to only track that one constellation. So it's become that term like tissue Kleenex kind of deal, where everybody knows what you're talking about. But it might actually be more complex than that. It might be it might be picking up more than just GPS. So modern receivers are picking up multiple different constellations, multiple different channels, multiple different frequencies, and all of that is coming into this one specific chip. And the way that this chip is made and built and where it's coming from is actually really important to understand. Knowing what different constellations can be picked up can help you decide, what manufacturer you want to go with. What type of, quality of data are you actually going to receive? What level of accuracy can you expect? It all comes down to that independent chip that's tracking your position and giving you, you're calculating where you are in the world. So this is the hub. This is the actual, the GPS of it. The GNSS is the chip. So as that chip receives those signals, it calculates that position and gives you, your position on the Earth using that triangulation. That's where it's all happening, is inside that individual chip itself. So that's a very important component for a GNSS receiver, knowing where you are. This is the nuts and bolts. So this on its own and independent could be enough for us to get a position. But there's a bunch of other things that we can do now to enhance that position, make that position better, make our position data collection more efficient, and everything else from here on forward beyond the board with a chip on it is just going to be enhancements on this simple base. So how do we enhance this base? One way we do it is by adding an RTK engine. In nerd terms, it's lots and lots of math and code. And I tell you what, way above my pay grade. One thing I can really say that these folks that write RTK engines have is a lot of time, a lot of patience, and a lot of understanding of how very specific environments and radio signals interact with one another, and also how you can utilize a differential correction source and apply it in different environments to give you a very, very precise and repeatable position. So the engine itself and how it's written, I never realized until recently just how important it is into getting the position you have. In fact, the logarithm tends to be almost everything. How that logarithm interacts with your chipset and interacts with your position and solution is truly what is the precision level. And there's different RTK engines. Certain manufacturers have even the ability within the user interface to change what engine you're using based on the environment you're in. So making sure that it is truly set up and applying that correction in the right way and giving you that precise position and giving you what you need in the field, really, really powerful and really powerful to leverage. And that's how we can actually achieve some of these centimeter level accuracy positions live in the field. Another component of hardware that's really, really cool, modern GPS and GNSS solutions have an IMU built in. So you may have heard this term IMU. It's the internal measurement unit. There's multiple different ways that these types of IMUs can be built and work. Sometimes they're accelerometers, sometimes they're gyroscopes, sometimes they're both, and they kind of interact and work together. And the size of them sometimes can change based on the sensor and the application. So essentially, to take out a little bit of it, the big thing that's happening with an IMU is it is understanding this is where I am now. And when I get moved or shifted or changed position, I now know where I am relative to where I was. So it's allowing me to see things like tilt. Where am I tilted? Where am I positioned? How off of level am I in a 360-degree rotation? So essentially, there's 3 different independent sensors within this chipset, if you will, that know exactly where that unit is pitched and positioned. This enables me on my GNSS device to be able to capture data in a multitude of different ways. It allows me to capture data when I'm not perfectly level. In the old days, a lot of times, and even in some cases today, we have surveyors or field data collection people that are outside looking at the bubble level, making sure that they're perfectly level so they can get a shot exactly where that rod tip is. Nowadays, with tilt enabled on and an IMU built in, I can take a shot with that rod tilted. It also allows me to do something called visual slam. Now, this is a term you may not have heard of. Slam might not be a term you've heard of. Visual slam specifically, we're going to talk about that in just a few minutes. So we're going to hit pause on that. We'll come back. Let's continue to look at the IMU and how it works with actually collecting a position when you're on a tilt. So yes, this is a GNSS receiver that has an IMU built in. And yes, he's actually getting a high accuracy precision point, and he's tilted beyond 90 degrees. In fact, in this case, he's actually about 110 degrees or more. So what's really cool is some of these modern solutions, not only do they allow you to do slow amounts of tilt, so that can speed up your efficiency. You're not having to bubble level everything. You can go out and be confident that everywhere you're taking a point, it's giving you the point where that rod tip is. It also allows you to open up your minds and say, hey, I can actually take points almost upside down. In some cases, pretty close to upside down, and get stuff that's off in different directions. And so the GNSS absolute position plus the IMU sensor fuses together to give us a precision point in really challenging and different environments. And there's a bunch of different applications on how an IMU can assist us. The next thing we're going to talk about is a precise point positioning. So the reason I'm talking about this here is because it is another component that's built into the chipset, that's built into the board itself. Multiple different receivers and different companies have a precise point positioning system built in, and they all have their own different brand names or different systems that they have set up. So Tursis, for instance, has their Tursis Advanced Positioning System. Trimble will have like their Trimble RTX solution. Multiple different manufacturers have multiple different ways of doing this, but it's all built into that chipset behind the scenes. So if we look at the chipset itself, what it's going to do is it's actually taking down signals and receiving specific signals from a specific set of satellites that allow me to receive corrections from a satellite. Now, some of you guys might be thinking, wait a second, hasn't the FAA and WAAS and those SBAS satellites been doing that for years? And you're right, they absolutely have. However, the level of precision that you can get with an augmentation system like SBAS or WAAS, we tend to normally spec that at sub-meter, maybe a little bit better in some scenarios. But sub-meter isn't always what we need. Sometimes we need much higher levels of precision. So we can tap into a service that allows me to get my corrections via satellite, not have to set up a base, not be reliant on a VRS network or anything along those lines. And I can actually get a high accuracy position just by tying into some satellites. So this is kind of a cool way. It's another method of receiving my differential GPS. And it could be something that could benefit you where you don't have to have a base, even if you're in a super remote location. Maybe you're mapping something up in the boundary waters where, you don't have a cell signal, and I need to be able to get a precise point. So there's some areas even in our own backyard where something like this might be of benefit. So now that we're going to move away a little bit from the actual board itself. So some of these components still tie into the board, but aren't directly built in or fused into the board. There are other sensors that are going to be within the same type of receiver. So in some circumstance, us GIS folks don't always cross paths with the surveyors. Surveyors traditionally know exactly what's going on with having an integrated UHF radio. For you as a GIS person to understand, another way we can communicate a differential correction position is via radio. So if there's a local base station that's broadcasting, or if you have a base station set up, you can broadcast on UHF radio. And what it's essentially going to do is give you a seamless correction directly to your receiver. So therefore, you're getting that high accuracy position live in the field, no post-processing necessary. Everything's coming into you live. So now you can not only navigate to and stake out certain positions you can also collect with accuracy and no need to post process. So when it's tying into your GIS immediately live in the field, it's tying in directly with where that point is, no extra steps, no extra work. So having a UHF radio can actually be really beneficial in a lot of different scenarios. But it also is another way that we could potentially enhance a position where we're at. So let's say, for instance, we are doing a survey in an area that has maybe some dense trees or maybe some spotty cell coverage. You can actually stack multiple types of differential corrections together, depending upon what software you're using, and actually have multiple ways that you can daisy chain from, hey, maybe I'm using the Minnesota VRS network, but if I lose cell coverage, it's going to fall back on my TAP solution, or maybe it'll fall back on my radio solution. So there's multiple ways that we can stack our differential correction source and allow us to always know that we're going to have a good high accuracy point anywhere we are in the field and not be reliant on another service. So if this is something that you're needing, know this is one of those options that are out there. And many of these modern receivers have that radio directly built in. It's no longer an external component. This might be another term that you've heard, NTRIP. NTRIP is a network transport of RTCM. RTCM is a language that's being used for differential corrections. So that source language, like GPS also has some source languages, GGA, multitude of other different languages that communicate that string across back and forth between technology. RTCM is just simply a language that's used to communicate from a differential correction source to your receiver. So NTRIP is the networked transport of that language and signal via internet protocol to your device. Essentially, this is what a VRS network is doing. Just like MnDOT's VRS network or the MnCore's network, we can take that position, we can log in via a cell signal, and we can immediately connect in, get that correction source, and get a high accuracy position out in the field. So that's going to be coming in via NTRIP. I just want to make sure you guys are familiar with that term, so if it does come up, you know what's there. So there's a bunch of different NTRIP components that need to be in my sensor in order to potentially get that receive that type of correction. So a SIM card can be directly built into a GNSS receiver. It can also go into, you could also potentially utilize your data collector or your cell phone. That might be another place that you're getting it, but it can also be integrated directly in. So as we're talking sensor stacking here, this is one more thing we can stack directly into that sensor and give us some of that built-in ability to receive corrections directly to that rover without needing it on our handheld. A 4G modem is actually built in directly into some of these receivers. What that allows us to do is to broadcast NTRIP. And now that we know what NTRIP is, we can broadcast corrections to a controller and now have RTK fix on our drones. So as long as I'm within proximity of my base station, I can transmit a local Wi-Fi or 4G type connection, bind my controller to it, fly my drone, and have an RTK survey happen, all because that is built into my receiver. Kind of another way to leverage things. There's also a thing called geocasting. Some GNSS receivers are built with geocasting enabled, which allows you to set up your own base station. So you're not reliant on a VRS network or some other agency running something for you. You can set up your own base station. If it's connected to the internet, another good use of why we can have a SIM card in our receiver or base station. We can now broadcast that up to the cloud. And then in that geocasting service from the cloud, as long as I've got access to internet, I can integrate directly with my base station. So now I'm not limited by some of the things that radio can get blocked by. So if I can be working on the other side of the mountain or on the other side of, further away than a radio could transmit, or underneath power lines where radio signals can get really messed up. There's a lot of different options and flexibility towards having something like a geocasting service directly integrated. And a lot of different manufacturers now are actually coming out with some systems that work along these lines. The last thing I want to talk about is throwing a camera onto the side of a GNSS receiver. Now, this is something that only a few different companies are doing at the moment. Tursus, I've mentioned Tursus before. Tursus happens to be the GNSS line that Vertex works with, manages, and sells. So I may, talk about some of these different components and different options that are in that line. So I'm going to talk about that just for 1 second here. So Tursus is one of the few manufacturers that actually has a camera integrated. Some others do as well, but this one in particular is one I'm most familiar with. What it allows you to do is a bunch of different new options and things that we weren't thinking about 5 and even 10, 5 years ago. What this allows us to do is do visual offset and visual slam. And I mentioned that term earlier. We're going to come back and take a look at what visual slam actually means. So let's take a quick peek here. Inside that camera, um, visual data collection, so visual SLAM itself basically means it's integrating a bunch of other different components. So it's integrating that IMU, the position that you're at, and the photos as they're taken. And it allows me to live with photos and photogrammetry, tie everything together so that each one of those pixels has a three-dimensional point. So what it's actually doing is making high density point clouds based on photogrammetry and based on the visual SLAM solution to be able to put a position on every single pixel that it can see with about 2 to 4 centimeters of accuracy. So in some of these GNSS denied or restricted environments, like the face of a building, underneath a bridge, I can simply take a quick walk, do a visual capture, and actually take those positions. Or I can generate a high density point cloud, an LAS file, and kick that off into my system. So let's take a peek at what that type of workflow looks like. So visual SLAM can be done by simply, this is visual SLAM with that offset specifically. I walk a quick survey. I live on my controller can hit, hey, take a quick or an advanced survey. It's going to do a very fast process on my actual data collector live in the field. I can then tap on and move around. We're seeing that with that blue crosshair in the middle there. I can tap and move around as to where I want to position my point, maybe right on that paint stripe. As soon as I am selected where I want, I can hit measure. I can measure a bunch of different points and hit store, and all those points get saved directly into my project, and they're going to be in a three-dimensional position X, Y, and Z. Really cool technology that allows me to visually capture and offset points into just something I can see in these restricted areas. Kind of a cool modern technology and a modern way of taking high accuracy positions. The other thing it allows me to do is collect that LAS live in the field. So as I'm walking along with this same type of survey here, that may even be the same survey, don't have to walk it again, it already did it. I can either select a section that I want to process or hit a different button and just say process everything. And I can take everything that it saw and live in the field process a high density point cloud. That point cloud can then come directly back in, and now I have a whole bunch of data that I can look at and work with. And so maybe if your field data collector was out there collecting a bunch of paint lines, if they happen to miss one, now you have it live in your controller. So when you're back in the office, you can be like, oh, well, I know where that is, and I can collect that point. So there's a bunch of different options and usability. Another thing that might be cool is maybe I need to do a quick volume calculation on a stockpile or a snow pile or something like that. I can quickly take some of this visual capture, create an LAS live in the field, push that back to my office user, and he can put it into some software that can consume an LAS. Maybe that's my GIS software. And I can very quickly calculate that cut and fill or that volume of that stockpile. A couple different applications there for you. So putting all of this together, all of these different components that make and create a modern GNSS receiver allows us to have built-in flexibility. We're going to increase our efficiency and our rapid data collection. So now I can walk out to a point and I don't have to worry about leveling things off. I've got an IMU. I know exactly where that point is because it knows where that tip is. I'm getting a superior level of accuracy in tough environments because I've got a bunch of different RTK logarithms working together, and those engines all work together to give me that position. I've got multiple different ways that I can get my correction source. So I can be versatile, I can be efficient, I can be flexible, and I can collect data pretty much anywhere I need. So these are all the components that we talked about within a modern GNSS receiver. So this is just that receiver that sits on a pole. But I've got a few extra minutes here, and I want to bring up one other thing. What happens if we change the form factor? So let's look at the same type of thing we've been talking about. Sensor stacking, all these different things working together to give you a solution. What happens if I add a LiDAR scanner and change the way that all these components work? Now I'm looking at a different type of device and a different type of platform, which is where I see a lot of things starting to go. You may be familiar with the term reality capture. If you haven't heard it, it's a term you're going to hear. There are certain consulting groups that now have entire departments completely dedicated to reality capture. What this is doing is this is taking point clouds, photos, GPS positions, GNSS positions, survey data, GIS data, slamming it all, no, bad term because that's an actual term for slam there. We're crunching that all together into one solution to actually give ourselves what we call digital twins, or a true digital representation of reality. So reality capture and reality capture devices can generally be captured using things like LiDAR or photogrammetry and RTK. All these things get stacked together to give you a solution. So you might see, so SLAM itself being that simultaneous location and mapping is using all those same components that we just talked about in our GNSS receiver, but putting it into a different type of platform and integrating a laser scanner or a LiDAR system. So let's look at what some of these results can do. If we use, like, for instance, a handheld scanner, we now have the ability to start maybe surveying with RTK precision XYZ located positioning. We can start actually getting 3D models into GNSS restricted areas and get point clouds in things like storm structures or sanitary structures. We can also start capturing things like parking garages and actually start integrating and doing thousands and thousands, and in some cases, actually millions of measurements in the matter of minutes. So for instance, I look at this survey here. I was able to do a quick one with the S1, a handheld survey. This is just actually on Friday. I went and walked a big parking garage and I collected millions of data points at a rate of 200,000 points per second. I was able to capture an entire parking garage in 20 minutes, process it, and now I can actually slice it, measure it, do all kinds of things to interact with it, and tie that directly in with my GIS data. Another term you might be familiar with in the GIS world, and a lot of the ways that GIS is transforming and moving, is some of this building information models or BIM modeling. A solution like this allows you to do interior mapping and take GPS completely out of the equation. So now I'm actually able to go indoors and map construction job sites. This is a construction project. I actually just did this scan yesterday. Walked around, and this is a construction site where a company is completely redeveloping stuff. We can actually look at the data, interact with it, take measurements, and store this, and get and integrate this into our building information models. The other unit, that S2 unit, that big backpack type unit, allows me to expand my distance. So an S1 and handheld unit, I'm kind of limited on how far my range is. I can only shoot up to about 150 feet. If I do that backpack unit, I'm now going to get more points per second, and I'm going to get a little bit higher level of accuracy. And I'm also going to get a much longer range, more like that 300-foot range. And so then I start to get some data sets that start to look like this. And we can really see how having data at this level of precision can really help out engineers and other departments that you're going to be working with as GIS folks. So if you're working for a utility company and you want to see that substation in absolute accuracy, we can do it terrestrially without ever even having to put up a drone. We can just walk around it very simply. This scan was done in 5 minutes, and it was actually done by a utility company. I mean, I don't have permission to walk around in a substation like this. So I trained him up in 3 minutes. He was able to quickly walk through with this backpack on, capture this data. We went down to Portillo's to pick up a hot dog, and we processed it all in 25 minutes. And here's your end result. Reality capture is starting to get really, really fun. We can also do big projects. We can do projects like scanning an entire complex. So now think about all the different things we just captured by walking this big site with tons of buildings around it. To do this with something like a terrestrial scanner, which works very well, is extremely accurate, it took 82 setups to do this site, and it took them almost all day long. I think it was about a 10-hour day for those surveyors. I walked the site in about 40 minutes, and all of my data is really, really close to what their data is. We're talking, and surveyors like to talk in tenths. All of my data was plus or minus a tenth, and in some cases it was tighter. Just a matter of all those different things. So SLAM is now becoming it was something that was there for a long time, and it has been there since the early 2000s. But with GIS integration, or excuse me, with GNSS integration and high accuracy points and new logarithms and new processing, a lot of those big issues that SLAM used to have, which were like drift and fuzzy clouds and fuzziness on walls, a lot of that is all starting to tighten up, and we're seeing really, really precise data and really, really fast data collection times. And because these buildings were actually so low, it almost looks like I flew this with a drone, but I can guarantee you I actually just walked it. If you look at that photo on the right there, that yellow line is actually my breadcrumb trail, and each one of those little balls is a photosphere that's showing me an image. So if we look at that left image, I'm actually clicked on one of those photospheres. You can see the photo in that right third, and you can see that that's the image that was being used to colorize the point cloud. I can see the actual photo itself. I can integrate directly with that point cloud. What a powerful tool to have as a reference for a project you might be doing. Really, really cool stuff with some of these different form factors of sensor stacking. Some of you may have seen this at the GIS LIS conference last year. This was one that the Vertex group scanned before I was there. They were able to scan the whole bridge in about 12 minutes. Really, really fast data capture. I think it took them about 45 minutes to process, and they processed it live at their booth at GIS LIS last year. Really kind of cool. So one other form factor, just to quickly touch on it, just because why not? We might as well. Let's think about how sensor stacking can work. What's that guy doing floating down there in the lake? We can also take this now to potentially integrate with high accuracy data collection and tie it in with a sonar scanner. So if I've got a sonar sensor directly on a boat and I'm tying that in with my GNSS solution, now I can actually do bathymetry surveys, soft sediment surveys, ponds. All this type of stuff can be done simply by running an automatic boat that I can program to run just like a drone nowadays. Where you mission plan it, you hit go, it drives itself, it comes back, you download the data. Very cool. We can actually then see that data in a sonar tool, which allows me to clean up. So, I mean, does anybody know that we have weeds in lakes here in Minnesota? So if we start to get some of those bad returns, we can see it in this sonar type of data return and actually clean some of that up and get some really good, accurate bathymetry data just by simply driving it with an autonomous boat. So a lot of different form factors all come in to where data capture, where reality capture, and where GIS data is being collected live in the field nowadays. And so I hope that this deep dive into what is actually happening inside the hardware, what are each one of these individual components and how do they work? I hope this gave you a little bit of insight into the technology itself, where it was, where it is, where it's going, and some of the potential. Maybe you can see where your company, your department is going to have questions, and people are going to ask about, well, what about this type of solution? Hopefully, this gave you some good knowledge and background on what the technology is doing, what the hardware is doing, and where things are going. So with that being said, I wanted to make sure I got done here at right about the 45-minute mark so that we had some time to have some interaction and questions. If you guys do have any questions for me, I would be more than happy to hear anything that you have to ask. And with that, I want to say thank you to the GIS LIS group. It's been an honor to be working with you guys for over a decade now. Thanks for having me on board to present on one of these mAppetite sessions, and thank you so much for the opportunity, Aaron.
Yeah, thank you. It's great having you. Um, we do have a few minutes here. If anybody has any questions, we can take some time to answer those. If you have any, just type them into the chat, and we will be sure to share those. All right. Well, while we wait, I did want to share a few events that are coming up with the consortium with the group. Um, Let me put some links in the chat. So our next Women in GIS networking event is taking place this Thursday. That's April 23rd from 5:30 to 7 p.m. That's at Modus Brewing in Minneapolis. Everyone is welcome to attend, and there's no registration. So just come on down and have a beer if you're interested. Um, Call for presentations for our 2026 conference are open. And abstracts are due on May 9th. So if you have any knowledge or experience or a project to share, we really encourage you to submit a presentation proposal. And more information is available in the link that I shared in the chat. Also coming up is our spring workshops. It's taking place on May 14th. And we have a pretty wide range of topics set up. So we really should have something for everyone. So we really encourage you to attend that. Registration information again is in the chat. Um, Next, we're currently accepting award nominations. So we're seeking nominees for the Lifetime Achievement Award, Polaris Leadership Award, Distinguished Educator Award, and our Emerging Professional Award. So if you have anybody in mind, please take the time to recognize them, and that information is shared in the chat as well. Um, Last two, if you're interested in presenting in mAppetites, the link is in the chat. Always looking for new topics and new presenters. And then finally, the last piece is that we are still looking to fill a nonprofit representative on the board of directors. So if you're interested or if you know somebody that might be interested, please just email that nominations at minnesotagislis.org. And I guess with that, looks like we might have a question. Sandy? Do we need to unmute
Oh,
Sandy or Sandy, can you maybe type your message in the chat?
looks like she's off mute now. Sandy, go ahead. Hmm, let's see if she can type it up. I noticed I'm still sharing my screen, and I got excited on the award nominees there. So in that recording, I guess you guys can you guys saw how I clicked on it and how easy it was to nominate somebody. So feel free to go ahead and fill that out too.
Yeah, really get in there and get some folks recognized.
Absolutely.
Well, Sandy, maybe we can reach out to you afterwards here and
Hmm.
get your question answered. We're not able to hear you, or I guess does anybody else have any questions for Roger? All right. Well, thank you again, Roger, and everybody who joined us today. We definitely appreciate your participation, and we look forward to some future mAppetite sessions.
Absolutely.
Thanks.
Thank you so much for the opportunity.
Yeah, thanks everybody. Have a good day.